prime factorization of 6 times 5 times 4 times 3 times 2 times 1 can be written in the form 2 to the power of a, 3 to the power of b, and 5 to the power of c, the value of a plus b plus c. Let's work with that. So 6 is 2 times 3. 5 is already prime. 4 is 2 times 2. 3, 2, and 1. So let's combine these all. So 2, we got 1, 2, 3, 4. Okay. And then for the next one, 3 is 1 and 2, I believe. And then 5 is just power. There's one power. And then this one, we don't count that since it's pointless. It's just a 1. And it's not prime also. So therefore, if we match it to there, 2 to the power of a times 3 to the power of b times 5 to the power of c, it looks to me like that a is 4, that b is 2, and therefore that c is 1. So they want a plus b plus c. So a plus b plus c is 4 plus 2 plus 1, and that is 7. So number 21, the answer is B. The ratio of the number of quarters to the number of dimes to the number of nickels in a jar is 9 to 3 to 2. If the total value of the quarters and dimes is $17.85, what is the total value of the nickels? So quarters to dimes to nickels is 9x to 3x to 2x. Okay. That is a sufficient way, I think, of writing it. I put in an x in there because we don't know exactly how many. It could be 18 quarters. It could be 27 quarters. I don't know. All right. So then $17.85 is the total value of quarters and dimes. So we have a certain amount of quarters, 9x. And each quarter, they tell you, is worth 25 cents, just in case you forgot. And dimes is 3x. And again, they've told you that they're worth 10 cents each. So we do this math here, and we got 1785 is equal to, what is that? 225 x plus 0.3x. So it's 2.55x is equal to 17.85. Okay. And then if we divide through 17.85 divided by 2.55, we get 7. Okay, that's great. So then what were we asked? Total value of nickels. Okay, so nickels is 2x. So 2x would be 14. And the value of the nickel, a nickel is worth 5 cents each. So it'd be 14 times 0.05, I should say. And that, I believe, is 70 cents. Yeah. So 70 cents, and that would be C. Five different integers, each greater than 0, have a sum of 264. The greatest common divisor of these 5 positive integers is D. What is the sum of the digits of the largest possible value of D? So we have A, B, C, D, and E, 5 integers, and they're different, and their sum is 264. Okay. And then we have a divisor that is denoted by just D. Okay. And then they want the largest possible value of this D. All right. Well, to get the largest divisor, we would have to have the smallest numbers, correct? Because if you're dividing by D, like that, the largest value of D would be obtained. If we want to maximize this, we'd have to minimize that. Is that right? I think so. Well, let's roll with it anyways. So let's just try to get the smallest possible values of A, B, C, D, and E. So, and they're all divisible by D, right? So I'll let A equal D. I'll let B equal 2D, because I'm trying to get the smallest possible multiples of D. 3D, 4D, and then E would be 5D. Yeah, I think that would probably make sense for now. Okay, so this sum therefore becomes D plus 2D plus 3D plus 4D plus 5D. And then that's still 264. And then remember, I think that's good enough. I don't want to make things complicated. Let's just stick with that. When you add this up, it's going to be, what is it going to be? 15D, right? It's 264. And then if you divide this, D becomes 17.6. Okay, but here's the thing. Let's see here. It's given me an exact value. Okay. I think I figured out what I did is correct, because I chose the smallest possible values of A, B, C, D, and E, right? So that means I've maximized the value of this D. So this is the largest possible value of D. So therefore, D is most likely less than or equal to 17.6. Well, obviously, because 17.6 is the largest. And is D an integer? I'm pretty sure. Well, yeah, I mean, D is going to be an integer. Okay, that's pretty good progress. So now how do I figure out what is the actual value of D? Well, tempted to use 17, but I don't think that's right, because I have to understand that 264 has to be divisible by D, and I think that is what's going to help me. 264 has to be divisible by D. So therefore, let's talk about what is 264 in terms of its divisors, right? 1, 2, 3, 4. Well, what is 264? 264 is 2 to the power of 3 times 3 times 11, right? So is it 8 times 33? I think so. Yeah, 88 times 3. Yeah. Okay, so therefore the divisors would be 1, 2, 3, 4, 6, 8, 11, 12, and it kind of keeps going from there, right? 22, 24, 33, blah, blah, blah. But the good news is that we don't care about the ones that are above 17.6, because D is defined or calculated as less than 17.6. So we only care about these guys. And they want the largest of those, which is 12. And then in particular, they want the sum of the digits of that. So the sum of the digits of 12 are 1 plus 2. And therefore, that is 3. So, interesting question. That would be answer B for this number 23. A network of pathways led from a single opening to 3 bins labeled ABC. If a ball is dropped into the opening, it will follow a path and land in one of the bins. Every time a path splits, it is equally likely for the ball to follow either of the downward paths. Ellen drops 2 balls, one after the other, into the opening. What is the probability that the 2 balls land in different bins? All right. So I think I'm going to have to, make it a little bit bigger, because I have to explain this. Okay, so let's talk about this. So a ball drops in here, and therefore we have a 100% probability that it goes there, correct? But then it has equal probability of going in either direction. So it has a half probability of going there and a half probability of it going there. Correct? Following so far. Okay, now this guy then breaks up equally into a quarter here and a quarter here. Correct? And then this guy also breaks up equally into a quarter here. It's the same spot, and a quarter here. These 2 guys are in the same location, by the way. Then we continue. This guy breaks up equally into an eighth here and an eighth here. This guy breaks up equally into an eighth here and an eighth here. This one breaks up equally into an eighth here and 1/8 here. And then finally, this one has only one way to go, so it just stays a quarter. Following so far, hopefully? And then whatever is here goes into A, so there's a 1/8 probability. Whatever's here, we got to go a little bit further here, I think. Wait. No, this one is fine. This one is fine. It's this one that I have to split, because this one only has one way to go. So I don't need to split that up. But this one need to split up. First of all, let me figure out what is 1/8 plus 1/8 plus a quarter, because that obviously needs to be calculated. That's 2 over 8. So that's going to be 1 plus 1 plus 2, which is 4 over 8, which is a half. Okay, so that really is a half. So that half gets split up into a quarter here and a quarter here. Okay, I got it. So then that quarter goes into C. So C, there's a 1/4 chance. And then for B, we have to add this guy with the quarter. So let's do that. 1 over 8 plus 1 over 8 plus 1 over 8 plus that quarter. So that's 2 over 8, right? So that's 1 plus 1 plus 1 plus 2, which is 5 over 8. So 5 over 8 was what goes into B. And let's just see, this plus this should equal this 1. 1 over 8 plus 5 over 8 plus 1 over 4, which is really 2 over 8. And that does indeed equal 1. Okay, so I am confident that I have done this correctly. Okay, so now I guess we can sort of go back and look at the question. So the probability of A is 1 over 8. The probability of B is 5 over 8. And the probability of the ball going into C is 1 over 4. All right? So that's very important, obviously. Now they want, what is the probability that the two balls land in different bins? Different bins. Okay. So, different bins. So, different bins could be like, well, we have two bins, right? We have two bins. If you have two balls, they have two possible places to go. And we have to figure out how many different possibilities there are. Now you could have AA, meaning both of them land in A, both of them land in B, or both of them land in C. Or you can have two different bins, A and B, or B and A and C, C and A, B and C, or C and B, correct? Are there any other possibilities? I think that's it. I think that's it. Okay, so two different bins would be these guys. I'm pretty sure that's true. Okay, so there has a couple of ways of calculating this. I'm going to do it the easier way, in my opinion, which is take the full probability, which is 1, and subtract from it the probability of this, and that will give me the probability of that. So the probability of getting 2 A's would be the probability of getting 1/8 times 1/8, right? Probability of getting 1A is 1/8, so 2 A's would be 1/8 times 1/8. Probability of getting 2 B's is 5/8 times 5/8. And finally, the probability of getting 2 C's is 1/4 times 1/4. So this looks like 1 minus 1 over 64 minus 25 over 64 minus 1 over 16. And let's see, hopefully I've done this math correctly. That'd be 1 plus 25 plus 4. I'm getting a common denominator, of course. So that looks to me like 30 over 64. And that looks like 64 over 64, so that'd be 34 over 64. And in lowest term, 17 over 32. Is 17 over 32 one of the answers? And it is. Yay. So, fortunately, all my madness up here worked out and got the correct answer. A figure is constructed using 14 1 by 1 by 1 cubes. 9 of these cubes are used to make the bottom layer, and 5 additional cubes are positioned on top of the bottom layer. The figure is shown from two different perspectives. An ant begins at P and walks a distance D on the surface of the figure to arrive at Q. The smallest possible value of D is closest to. All right, well, first I'll show you what I think, and then we'll see if it is correct. But somehow I think my initial thought is wrong. The reason is because my initial thought, I think, is too simple. And here's my initial thought, that if you want to go from P to Q, like in the shortest way possible, we would just initially just go from here to here, and then we would just continue to go in a straight line from that point to Q. And if we opened it up, meaning if we were to, say, put them side by side. Let me just draw it in a crude way to illustrate what I'm talking about. So this is this side, right, where the P is here. And the other side, I'd flatten it out. So like that. I'd flatten it out so that you can see. And this is Q here. So really all I'm doing is I'm basically saying just take a straight line from P all the way to Q, and there you go, you're all done. And then you'd calculate that fairly easily with Pythagoras. So this side is 1, 2, 3, 4, 5, 6, and that side is 3. Is that right? So P to Q squared would be 6 squared plus 3 squared, and then that's 36 plus 9, which is 45. So therefore P is root 45, which is approximately 6.7. 6.71. And then you say, okay, it's C, and I move on. Well, I'm done actually. But because it's number 25, I don't think it's that simple. I wish it was. And the sad reality is that it's not that simple, and it's not C. So you think, okay, not a problem. It's number 25. Obviously, it's going to be challenging. So how do I do this? How do I get a number that is smaller than 6.71, right? And all of these other answer choices actually are smaller than 6.71. Okay, so this is how we do it. You have to figure out a path from P to Q that is smaller than this method. So here we go. I'll illustrate it with some diagrams. So this is the path you want to take. As you can see over on this side, we're going from P to Q, but in this real zigzag way to kind of minimize our distance. And then they show another angle here, another view, I should say. Same path, but you get to look at it from a different angle. Now, you think, well, how on earth do I figure this out in terms of the distance? Well, that's where the other diagram comes in. All right, so let's explain this now. This next diagram basically flattened out everything. So this right here, this cube, or this face, represents this guy right here. Okay? And the line that has been drawn is the same, as you can see. Then what they have done is they have taken this second face, this face, and then the face that's on top, and flattened out the top one, as you can see. And what that does is allows you to continue that path in a straight line, as you can see, where the red is representing the straight line. Then they just keep doing that. They keep doing that for the next one. The next one, of course, is 3, where this is the face of 3, right there, right? But the other diagram probably is better to talk about 3, because as you can see, it's the path continues on that side of that cube, and then the path continues at the back, if you can see. So those two faces are represented here, right there. And that allows you to kind of continue your straight line. And then when we get to 4, the fourth cube, the path continues on the bottom face, as you can see, and then the path continues on the, let's see here, boy, bottom face, and then it looks like part of the back face right there. So that's what these are. And that continues there. And then finally, the very last one is the 5th cube, and it looks like the path is, it looks like here. It's at the, on this diagram, it's sort of like we're facing it. On this diagram, it's on the back. So I guess it depends on which angle you're looking at it from. So then that is represented just by this one face, and then the line continues there. So that is the actual straight line from P to Q, done in a very zigzag way on these diagrams. that essentially it's the same diagram, just you're looking at it from different angles. Now this P to Q, if we were to make this into a square, this side is 1, 2, 3, 5, and this side is 1, 2, 3, 4. Now, if we were to figure out PQ, it would be PQ squared is 5 squared plus 4 squared, and therefore PQ looks to me like 25 plus 16 is 41, so root 41, and root 41 is approximately 6.4, so 6.4 is the answer, and that is B for number 25.